Hello everyone, welcome back to the Atharva GATE Academy. Myself Chinmay Daduk. In previous video, we have completed the GATE questions up to chapter 4. Now in this video, we are going to start solving GATE questions of chapter 5, that is strain energy. Now this is very small chapter, so questions from this chapter is very less. So in this video, we will discuss questions from chapter 5. This first question is from year 2002. The total area under the stress strain curve of mild steel specimen tested up to failure under tension is a measure of ductility, stiffness, ultimate strength or toughness. In the theory part, we have discussed this point. We have discussed that total area under stress strain curve up to failure is toughness, or we can say modulus of toughness, but there is no option of modulus of toughness. So here we will choose option D, toughness. So you can remember that total area under stress strain curve up to failure is toughness. And here if we draw the stress strain diagram for mild steel, so it is like this, and this total area is this area. Fine. This next question is from year 2007. A stepped steel shaft shown below is subjected to 10 Nm/meter torque. If the modulus of rigidity is 80 GPa, the strain energy in the shaft in Nm is dash. In this figure, you can see this stepped shaft, and actually we can consider this shaft as combination of two bar connected in series. And here we apply this twisting moment, or we can say torque of 10 Nm/meter at the end of this combination of shaft. Here diameter of this shaft is given. Let's say this shaft is shaft 1 and this shaft is shaft 2. So here diameter of shaft 1 is D1 is equal to 50 mm and D2 is equal to 25 mm. Here length of both the shaft is also given. L1 is equal to L2 is equal to 100 mm, right? Now see, we know that how to find strain energy in the case of torsion loading condition. We know that U is equal to 1 by 2 T into theta, right? And theta is equal to TL by Gj. So actually U is equal to T square L by 2Gj, correct? So this is the equation that we are going to use in this question to find out total strain energy. In this shaft, total energy, that is U, is equal to U1 plus U2, means strain energy in shaft 1 due to this twisting moment plus strain energy in shaft 2 due to this twisting moment T. Fine. So here this U1 will be T1 square L1 divided by 2J1 G1 plus T2 square L2 divided by 2G2 J2. Now in the question, diameter is given and we know that J is equal to pi by 32 d raised to 4. So we can find out J1 and J2, right? L1 and L2 is given and G1 and G2 is same, that is given as 80 GPa. So here we only have to find out T1 and T2. Now what will be the value of T1 and T2? T1 and T2 is the twisting moment in shaft 1 and shaft 2 respectively. Now if you want to find out T1 means twisting moment or torque in shaft 1, then we will take one section like this in the shaft 1 and we will take summation of all the twisting moments or torque acting on this combination of shaft either side of this section. Now on the left side there is fixed end, so there will be one reaction at this fixed end, right? And here if this twisting moment is in the clockwise direction, so here it will be in anti-clockwise direction, right? But here we will take right side of the twisting moment to this section. So on the right side there is only one twisting moment, that is T is equal to 10 Nm/meter. So here T1 is T, that is equal to 10 Nm/meter, right? And similarly if we want to find out twisting moment in shaft 2, then we will take one section in this shaft 2 and we will take summation of all the torques acting on this shaft either side of this section. And right now we will take right side of the twisting moment or this torque. so it is also T, right? So here T1 and T2 is also same, that is T. So from here we can say that T1 T2, L1 L2 and G1 G2 is same, so we can take common. So it is TL by 2G into bracket 1 divided by J1 plus 1 divided by J2. So it will be U is equal to this T, that is 10 Newton into meter. So it is 10 into 10 raised to 3 Newton into mm, right? Here we will take twisting moments in Newton into mm. Now length is given as 100 mm. So it is into 100 divided by 2 into this G is given as 80 gigapascal. And here we will take this value of G in megapascal, or we can say in Newton per mm square. So it will be 80 into 10 raised to 3 megapascal, right? And here this J1 and J2 will be found out from this expression. So here we can take this pi by 32 common. So it will be pi and 32 here, right? Into bracket 1 upon d1 raised to 4 plus 1 upon d2 raised to 4. And in this expression this d1 is 50 mm and this d2 is 25 mm. So here you have to put these values and you have to find answer of U. And here if you will calculate this value, then you will get answer 1.73 and this answer will be in Newton into mm. And here this answer is also asked in Newton into mm. So here we have to choose option C. So this simple question is for 2 marks and I hope that you understand this question. Fine. Now this next question is from year 2008. The strain energy stored in the beam with flexural rigidity EI and loaded as shown in the figure is dash. In this beam we have to find out total strain energy stored in this beam due to this loading condition shown in this figure. Here this is the simply supported beam and this 2-point load P are acting on this beam at a distance of L from these ends. Now how to find strain energy stored in this beam? We have discussed in the theory part that to find the strain energy in the bending loading condition we have to use equation integration mx square divided by 2EI into dx, right? This is the equation to find out strain energy in the case of bending load. And here in this beam, due to this load, there will be bending moment produced in this beam, right? So here we have to use this equation. Now see, here we will take this part as part 1, this part as part 2 and this part as part 3. And let's say at this point we take origin where x is equal to 0 and this right direction as x direction. So here we have to find out total strain energy, that will be summation of strain energy in part 1 plus strain energy in part 2 plus strain energy in part 3. And here you can see that this beam is under symmetrical loading condition, right? Means if we see this beam about this midpoint, then it is actually symmetrical about this axis, right? So here we can say that strain energy in this part and strain energy in this part will be same, right? So here we can say that it is equal to 2u1 plus u2 because u1 and u3 will be same. Now see, here we have to find out mx, means bending moment as a function of x, right? So first of all we will find value of this bending moment in this first interval, that will be interval 0 less than or equal to x less than or equal to L, right? And in this interval, if we want to find out bending moment, then first of all we have to find out reactions at these two ends, right? And as we know that this loading condition is symmetrical, reactions at both the ends will be same. And here these reactions will be P and P, because total load in downward direction is P plus P, that is 2P. So total load in upward direction should be to P. And for that we have to take P load here and P load here. So actually these reactions will be P and P, right? And you can also follow same method of sigma F is equal to 0 and sigma M is equal to 0, and you can find out these reactions, right? Now see, if we want to find out bending moment, then first of all we have to find out F, and for that we have to take one section in this interval at a distance of x from this origin, and at this section we have to find out shear force. Now if we want to find shear force, then we have to take summation of all the transverse force acting on this beam on the origin side of this beam, and on the origin side there is only one transverse force, that is P, acting on this beam, and it is in the upward direction, so shear force will be positive P. And bending moment is integration of shear force, right? So bending moment will be Px plus C, and we know that at point x is equal to 0, value of bending moment is 0. So actually value of C is 0. So equation of bending moment is M is equal to Px. So now we have Mx is equal to Px in interval 0 to L. Now we will find value of Mx in second interval, that is L less than or equal to x less than or equal to 2L. And if we want to find out bending moment in this interval, then we have to take one section in this interval at a distance of x from this origin, and here we will find shear force, that will be summation of all the transverse forces acting on this beam on the origin side of this beam. And on the origin side there are two forces acting on this beam. One is this reaction, that is in the upward direction, so it is plus P, and this load P is in the downward direction, so that is minus P. So here shear force is 0 in this interval. And if we want to find out bending moment, then we have to take integration of shear force. And if we take integration of shear force, then it will be 0 plus C, right? Here there will be constant C. And now if we want to find out this constant, then we have to take one boundary condition in this interval of this beam. Fine? Here this is M is equal to C. Now see, in this interval, means from here to here, we know that at x is equal to L, value of bending moment will be P into L, right? Means at this point we have find out value of bending moment. From this expression, at x is equal to L, bending moment will be P into L. And here if we will put this condition in this equation, then we can say that M is equal to P into L at x is equal to L. And here there is no value of x in this expression, so it is actually equal to C. So here value of C is P into L. So we can say that bending moment is P into L, and that is constant in this interval from here to here. So here we can say that Mx is equal to PL in this second interval. Now we have value of Mx. So we can find out value of total U by finding out U1 and U2, right? So here if we will put value, then it will be 2 into U1, that is integration of Mx square, that is Px square, divided by 2ei into dx, and here this integration will be from x is equal to 0 to L. So it is from 0 to L. Plus U2, that is integration this Mx, that is P into L, so it is PL square divided by 2ei into dx, and this integration will be from x is equal to L to 2L, so it is from L to 2L. Now see, this is the simple integration that you can do by yourself, right? And if you will find the answer from this equation or from this expression, then it will be 4 by 3 P square into L cube divided by 3ei. Means here answer is option C, and this question is for 2 marks. So I hope that you understand this question. Here first of all we are taking 3 intervals, and we know that these loading conditions are symmetrical about this point. So strain energy in this first part and this third part will be same. and this total strain energy is equal to U1 plus U2 plus U3. So it is 2U1 plus U2. And we have the equation to find out U for bending loading condition, that is mx square by 2EI into dx. Here we only have to find out mx in this first interval and second interval. In first interval it is easy to find out this bending moment, right? But in the second part it is little bit difficult. But I hope that you understand this method to find out bending moment in this second interval. And you can also use another method to find out directly bending moment at this section. You can directly take summation of moments by this P load and this P load. If you take moment by this P load, then it will be P into this distance, that is x, right, from this section to this load, and moment by this P load will be this P load into this distance, that is this x minus L. So it is minus P into x minus L. This P load is in the downward direction, so here I have taken negative sign. So from here also it will be P into L. Fine. So you can also use this method to find out direct bending moment in this section or at this section. Now this next question is from year 2016 paper set 1. A hypothetical engineering stress strain curve shown in the figure, and it has three straight lines PQ, QR and RS with coordinates P, Q, R and S, that is also shown in this graph. Q is the yield point, R is the UTS point and S is the fracture point. Here we have to find out toughness of the material in megajoule per meter cube. Now see, in the first question of this video we have discussed that toughness is equal to area under stress strain curve up to fracture point, and here S is the fracture point, so this point is fracture point, and to find out toughness we have to take this area under this stress strain curve, so we have to take this whole area. Now see, here all the points are given, we only have to find out total area. Now here notice that this strain are given in percentage, so here we don't have to use this value of strain in this equation, we have to use original value of engineering strain, means we have to divide all these values with 100 in order to find out original value of engineering strain, because these values are given in percentage. Now to find out this area, we can divide this area in three parts, 1, 2 and 3. This is 1, 2 and 3. Here it will be A1 plus A2 plus A3. Now it is simple, right? This area of triangle will be 1 by 2 base into height. This base is 0.2 divided by 100 into height is 100. Plus area 2 will be 1 by 2 into 100 plus 140 into this distance, that is 0.6 minus 0.2, 0.4 divided by 100, plus area of this third part will be 1 by 2 into 140 plus 130 into this distance, that is 0.8 minus 0.6, that is 0.2 divided by 100. Right, so now if you will calculate this value, then you will get answer of this question, and this answer will be 0.85, and unit of this area, or we can say unit of this toughness, will be megajoule per meter cube. Here why this unit is megajoule per meter cube? Here if you see this unit, then it is mega into this joule is Newton into meter, right, divided by meter cube, so it is actually mega Newton per meter square, and we know that Newton per meter square is Pascal, so it is actually mega Pascal. And see, here engineering stress is given in megapascal, and there is no unit of this engineering strain, right? So unit of this area, or we can say unit of this stress, will be equal to unit of this toughness. So here we have to write answer 0.85, and that is toughness of the material. So this simple question is for 2 marks. Here we only have to find out area under this diagram, and here we have to take care In the value of engineering strain, we have to divide this value by 100 because these values are given in percentage. Fine? Now this is the last question from this chapter. This is from year 2017 paper set 2. A cantilever beam of length L and flexural modulus EI is subjected to a point load P at the free end. Here we can consider this cantilever beam and there is one point load P acting on this beam. Here length of this beam is L. The elastic strain energy stored in the beam due to bending neglecting transverse shear is dash. Means here we have to find out strain energy stored in this beam by this bending load produced by this point load acting on this beam, right? Now we know the equation to find out U, that is integration of mx square divided by 2ei with respect to x. Now here this ei is the flexural modulus that is given. We only have to find out mx, that is bending moment in this beam as a function of x. To find out mx, we will take this point as origin where x is equal to 0 and here we will take this direction as x direction. So at this point x is L, right? Now if we want to find out value of mx in the interval of 0 less than or equal to x less than or equal to L, then we have to take one section at a distance of x from the origin and we have to find out bending moment at that point. So here we can directly find out mx, that will be this p load into this x distance, that will be p into x, right? So we will put this px instead of mx. So it will be integration px square divided by 2ei into dx, and this integration will be from 0 to L. Now see, this is the simple integration that you can perform, and if you will perform this integration then you will get answer option D, PL cube by 6ei. Fine. So that is the answer of this question, and this simple question is for 2 marks. So I hope that you understand all the questions from chapter 5. If you have any doubt, then you can tell me in the comment box. And also you can see that these questions are very less from this chapter because this chapter is small chapter, right? But it is important and it is very easy also, because in this chapter you only have to understand some concept and you only have to remember few formulas, right? Now today we are going to stop here, and in the next video we will start with next chapter. If you like this video, then make sure that you hit the like button, and also share these videos with your friends and classmates so that they can also get benefit from this channel. Now we will meet in the next video. Till then, stay motivated and happy practicing.